Let's start. Bismillahirrahmanirrahim. So this is about lesions of the descending tracts. So this circuit diagram will be shown quite a lot. Then you will see pictures like these, uh, terms like these, decortication and decerebration. Mind you, these are the two main terms that we'll be discussing today. These are the two main terms, especially decerebration, that comes in your exam. Okay? If you understand this diagram, if you look at this whole patch here, this whole patch, this is the cortex, this bit here, cerebral cortex. Okay? This dotted line is the cerebral cortex. Forget about the D and the A. Just look at the dotted line. Okay, this is representing the cerebral cortex and the cells of the cerebral cortex. Okay? Then you have another dotted line here. This is a level of the brain under the cerebral cortex. So this is a subcerebral cortex sort of level. Okay? This is the topmost part of the brain. Then you have the part which is under this cerebral cortex. Then you have the brainstem here. Okay? You have the cerebellum on the side, and then as you go along further down, I'll just zoom out for a bit. Here you have the muscles, the recipient of the whole program. Do you see the orientation now? Beta spinal cord is represented by these fibers, and if you can see that these are the motor neurons. Okay, I'll go in detail, but these are the different type of motor neurons. They reside in the spinal cord, and if you look closer, he has shown one type of extensor muscle and one type of flexor muscle. Okay, this is a flexor muscle, extensor muscle. Okay, look at the way the fibers have been made. Okay, so there are these two fibers, symbolic fibers, which start from the cerebral cortex and end in the on top of the tracts that we read yesterday. Which were those tracts? The tracts were reticulospinal, okay, fibers, pons, reticulospinal fibers, medulla, okay. Then we had corticospinal fibers. Then we had rubrospinal fibers. And final point was vestibulospinal fibers. Now you see you can also, this is a good diagram because you also see the anatomical connections without the jargon of anatomy. So it's just bare bone picture showing who is where is the exact address when we're talking about the function. Okay? So if you've understood these fibers, let me just recap. So there are short fibers, these two. This is cerebral cortex communicating with the reticulospinal fibers. Okay, so it is stimulating. The plus sign is stimulating. So cerebral cortex is stimulating the reticulospinal fibers here and here. Then you see that you have the cerebral cortex sending its longest fiber, the corticospinal tract, right down to the level of the spinal cord ventral horn motor neuron. Right here. Okay. So if I were to zoom this in, corticospinal tract, it came from the cerebral cortex directly, no other business in the middle, came directly on top of this neuron. I can tell you from here, you can't see it, but it's a flexor alpha motor neuron. Okay, going to the flexor muscle. So the corticospinal tracts go directly or on either the interneurons of the spinal cord or directly on the alpha motor neuron of the ventral horn, which are innervating skeletal muscles directly. What is left is this guy now. Well, guess what this is? This is the red nucleus. Okay, this is my cursor. And the cerebral cortex fiber communicates with the red nucleus through short fibers. And then there are short fibers running from the cortex called the corticorubral fibers, which end up directly on the red nucleus. They stimulate it, okay? And from this nucleus, you have the rubrospinal tract going down and again to the flexor alpha motor neuron. Let's move on. Now, I'll focus here on this bit here, okay? As you can see that corticoreticular fibers these are corticoreticular fibers, these two that he has depicted. Remember, this is a schematic diagram, guys. This is not just two fibers. There are thousands and thousands of fibers like this coming down, and these are not just one nuclei, they have many nuclei, okay? So anatomy will be grinding you on these details very soon, hopefully. And they'll be thanking us because we have done the spade work for them. They just need to come and really just revise these bits with you. Anyhow, so these cortico-reticular fibers, they come down on top of these reticular nuclei. One is, this is now additional information. So you have the excitatory reticular formation and the inhibitory reticular formation. The cortex stimulates the excitatory fiber, which is excitatory to the extensor gamma motor neuron. This was the flexor alpha motor neuron. Now the green thing is the extensor gamma motor neuron. Please mind the difference between two of these neurons. They are different. Alpha motor, gamma motor. When the cortex stimulates the pons reticular formation centers, they are basically excitatory in nature because they excite the extensor neurons. So this stimulation leads to excitation of the extensor neuron. However, here is inhibitory. These are inhibitory neurons by their nature, as you can see right here. They are inhibiting the same neurons, ventral extensor neurons, gamma efferent neurons, okay? To keep a check and balance on the stimulation. You will see a lot of this in CNS. Something is being stimulated at the same time, it's also being inhibited. These local circuits are there to keep a balance so that whatever the target neuron is, it doesn't go beyond its scope, okay? So you have a very tight kind of regulation right at the level of neurons in CNS. It's beautiful. It's intricate, but it's beautiful. It's controlling the controller, if you know what I mean. Anyhow, so cerebral cortex by stimulating an inhibitory nucleus, an inhibitory fiber, actually increases inhibition. So although this is a plus, but eventually this plus will stimulate a inhibitory fiber, enhancing this minus. Do you understand? This will help you understand cerebellum one day as well. This is just to tell you the skeleton of this, the whole circuit diagram of this. We will manipulate this later on. Okay? Very important point, this guy here. Please make a note of this straight away. What is this? This is the ascending sensory fibers via ALS. There's the sensory fibers, the sensory information ascends, right? We are on the descent now, but Dr. Noora would have taught you that sensory information goes from effector organ upwards. There are two ways, there are two main tracts of this sensory information. One is the ALS. So anterolateral means it is placed anterolaterally in the spinal cord. So no rocket science here. Okay. This ascending fiber, while it was minding its own business going through the brainstem to the upper areas and eventually telling the cortex of the wonderful experiences that the muscle is having, okay, and the surrounding fascia, it gave an excitatory branch here, right here. it's a it's a it's a point here, right? So this excitatory fiber is given to the excitatory pons center of the reticular formation. Sort of gives it a wake up call. I'll give you an example. You will understand what is going on. Sensory information, which basically had little to do with descending motor output of the motor cortex. But here you have an evidence that it does have something to play. Okay? Here you have a crossover of the two worlds, sensory going up, motor going down. Okay, and you have proof that it becomes a bit naughty here and tickles the excitatory reticular formation nucleus, which is, by the way, excitatory to the gamma. It and is being excited by the cerebral cortex in the first place. This also excites it. Okay, if this you have understood, let me quickly ask you a question. I mentioned the crossing over of the two worlds, sensory and motor. I taught you a point yesterday about this crossover at a separate place. Do you remember that separate place? This guy, corticospinal tract. Still no? Remember we talked about its composition, Einstein's? And I mentioned to you that a good solid fraction of the fibers, sensory fibers, constitute the corticospinal fibers. So there are crossovers between the sensory and the motor. That was the point. Okay? I'll walk you through it. If you can just see the tracts going in and out and the color scheme. This is green. This is blue. This is red. Yeah? You see the main things. This he has shown, as I mentioned, a gamma motor neuron. Okay? The gamma motor neuron comes here and goes into your extensor muscle and innervates the tapering end of the muscle spindle. Nothing new, I hope. If this is new, you seriously are in the wrong class. Okay? So gamma efferent coming here, going into the muscle, minding its business, right, going to the muscle spindle, tapering end, and that's that. And you know what gamma efferents do. Okay? From there, you see the red stuff. This is the sensory fiber emanating from the muscle spindle, going to the dorsal horn and coming into the synapsing with the alpha motor neuron. We are just completing the circuit diagram for the stretch reflex now. Sensory afferent originating from muscle spindle, going through the dorsal root into the spinal cord, synapsing the only monosynaptic reflex that you've read up till now, probably the only one that exists, directly onto a motor neuron, which, by the way, is an extensor alpha motor neuron. Okay, you already know this. We read this in knee jerk. Okay, quadriceps femoris is an extensor of the knee, so nothing new there either. Okay, so this synapses here, and this alpha motor goes to the extrafusal element of the same muscle. Nothing new. So mind you, I am now moving my cursor in a circular fashion. This, bache, is the reflex arc of the stretch reflex. Is it not? Mr. Lonely flexor alpha motor neuron. It's right here. Okay. It is going to the lonely flexor muscle on the side. Nothing fancy going on here. What I was saying was, an immediate cache of knowledge is waiting for you right here. Check this out. See that the gamma family is under the reticulospinal tract influence. Okay. You see the flexor alpha is under the influence of the corticospinal and the rubrospinal. Extensors are under the brainstem tracts. I mentioned this yesterday. Hopefully you remember. Flexors are under cortico and rubrospinal tracts. Finally, extensor alpha again is under the influence of vestibulospinal, which is a brainstem level of descending tract. Okay, this was scattered information yesterday, but today you see it in a line. So I hope that this consolidates your understanding. This is the cerebellum. Okay, let me go free here. This is the cerebellum. Oh, by the way, I missed out the vestibular nuclei. It's part of this, not anatomically, but physiologically speaking, it's part of the cerebellum. I want you to focus on the vestibular nucleus. Here, what's going on here? Looking at the vestibulospinal fibers coming from the vestibular nuclei, and terminating on the extensor alpha motor neuron. The cerebellum is inhibiting the vestibular nucleus. Okay, and there are all sorts of negatives here. Okay, so it's suffice to say at this point where we have not formally read the cerebellum, that cerebellum basically inhibits the daylights out of vestibular nuclei. Okay, vestibulospinal fiber is to stimulate this extensor flexor, which it does. Cerebellum won't have it. Cerebellum is continuously inhibiting this neuron. Okay, so it is being kept in check by the cerebellum. All right, let me say it in one other way, shall I? If I were to cut the cerebellar influence, inhibitory influence, if I were to get rid of this cerebellum here, what do you think will happen at this point, the extensor alpha? It would be released from the inhibitions of the cerebellum, would it not? This is free now. So it will go into overdrive. Yes. Well, guess where it's going? It's going into it's basically supplying the extrafusal fibers of the extensor muscle. Okay? So what will happen in the extensor muscle? They will become overexcited, extended, tense. Can we say spastic? Spasm. If you disturb the cerebellum, spasticity ensues. What is spasticity? Let me say it now so that it stays with you. Spasticity is when you overstimulate a muscle, and this overstimulation causes a functional disability of the muscle such that it cannot do its job. We call it spastic paralysis. This is why we say that physiology is the basis of medicine. We just discussed spastic paralysis, but there is a flaccid paralysis as well. Flaccid is when you cut the nerve. So all of this is upper motor neuron lesions. When you do a lower motor neuron lesion, you cut the nerve. You cut this nerve here. You cut it. When you cut this nerve, this muscle will again go into paralysis. But what kind of paralysis? The overexcitatory type. You've denervated it. It will go into flaccidity. So that paralysis is also a paralysis, but that is of the flaccid type. Sahi hai? This is a big question, Viva question and MCQ question. What type of paralysis happens in upper and in lower motor neuron lesions, and why? Final point before we go on our very well-deserved break. It's a trick. So stay with me. Focus on this. Focus here. This is the gamma efferent neuron. Let me say if I were to overstimulate it this here, forget about the inhibitory arm. I've just knocked it out. I'm overstimulating it somehow from this circuit, and this really has become very angry. Tell me what will happen to the muscle because of this harkat and why. Noor and Abdullah were spot on. The muscle will go into spastic paralysis. Do I need to explain that, guys? By the exaggerated stretch reflex, that this overdriven gamma efferent it will keep stretching the spindle. The sensory fibers will keep sending stretch values input into the spinal cord, and the motor neuron will keep contracting the extrafusal fiber. This is like a perpetual positive feedback loop here, which will keep on overexciting the extensor muscle, and it will go into spastic paralysis. By the way, also call it the gamma loop.